everyone, today we are going to focus on finding the inverse of a function and in particular restricting the domain of a function so that its inverse is also going to be a function. So to start this off, we are going to talk about this graph here of this function, or the function here 2.5 times x minus 5, and it's given the distance in miles of a search and rescue helicopter that can travel within x minutes of reaching an emergency call. So again, we're going to talk about the original function and then its inverse function, which you'll see the definition over here. Basically, a lot of the big key components of an inverse is that the domain and the range flip-flop in a function versus its inverse. So if we start plugging in these x values, so if we plug 7 into this equation, we end up getting an output value of 5. And if we plug 9 in, we end up with 10, and 11 in, we're 15, and you're possibly seeing this pattern that's arising here from our linear equation. Now, even without knowing what the inverse function is for this particular one, we know the values in this table because the x and the y values, the domain and the range, they flip-flop. So now the range of our function is the domain of its inverse. So this also means for us then, when we graph this function, what we're going to notice is that they are reflections of each other over the line y equals x. So if you look at the top of the next page, on page 109, what we're going to see is this appearance that they are aligning to each other. And the other thing that we notice is that not only are they a reflection over y equals x, but what we also are going to notice is that the point x comma y on graph f of x is now y comma x on f of negative x. Okay, so again, we know that if, for instance, at 53 minutes, you're traveling 120, what we know instead is that f inverse of 120 would have to be 53 because, again, they're going to flip their points because they're inverses of one another, right? Now, f of 53 in this situation, if we're talking contextually with this problem, f of 53 is the number of miles that are traveled in 53 minutes. But if we flip this around, the f inverse of 120 means that we're going to look for that output value is going to be the time it takes to travel 120 miles, aka that output value of 53 minutes. Now we actually can find the equation of f inverse, and we can do that by looking at those points on the graph. So we have these points here that we know are lying on that graph. For instance, 5, 7 and 10, 9. So if we take those 2 points that we know are on that graph, in order to write the equation of this line, we can first find the slope. So y minus y, x minus x, we end up with 2 this, aka 0.4. And then using point slope form, y minus y, 1 equals m times x minus x1. Bringing this back from your equations of line days, we have our slope now is 0.4, and then we can pick either of these 2 points. I'm going to choose 5, 7 is my x1 and my y1. And as we distribute and solve, we end up with 0.4 times -5 is -2. Add the 7, we have this equation. Oops, 4x plus 5. We end up with that equation here. Now, what happens though if we don't necessarily want to constantly look at the input and output values, and what happens if it's no longer a line and we don't know necessarily that short to write it in? Well, this is where the idea of inverses comes into play. And a reminder, in inverse, the reason we talked about compositions is inverse functions, whenever you take the compositions of each other, this is the only time they're commutative, is because they both reduce to be simplify to be x, right? So if we tested this out, what we would notice is that these guys are in fact inverses of one another, because when we take their compositions, f of g of x and g of f of x, in this case of both of those functions, end up resulting in x, right? That's going to be our function. And we could test that out for f of x and f inverse of x, but I'm trying to save us some time to move on and see then how do we find this for more than just a line, right? So example A is really, really important, because notice this initial graph here is of a quadratic. And if we are going to be a function, right, functions have to pass the vertical line test, which this does. Okay, this passes our vertical line test. The problem, however, is its inverse, in order for it to pass or to work, it needs to pass the horizontal line test. So right now, our graph does not pass the horizontal line test. So what the conclusion we would have here is that the inverse would not be possible, because it wouldn't be a function. Its inverse wouldn't pass the vertical line test. So an important feature here is that what we need to do is, beyond recognizing that the inverse right now isn't a function, in order to make it one, we need to restrict the domain. So you have two options here. You can either restrict it so that you have all of the x values greater than 2, or you could officially also do all the x values less than or equal to 2. But if we restrict it to just half of this, okay, now the inverse is going to exist, because if we ignore this piece here, it will now pass the vertical line test, okay? And then from there, the steps are not too bad to actually solve. You just you replace f of x with y, switch x and y, and then resolve your equation so that you get y by itself. So notice here, we're just taking the algebra to, again, isolate y, and once you get there, it's now your inverse, okay? And notice if we graphed this, it would in fact pass the the vertical line test, because we have restricted it. So this is what our graph would look like. And again, these are reflections over the line y equals x as well. So again, that's why limiting that initial domain is super important, okay? So each time you do these questions, you want to make sure you look at the original graph first, okay? I cannot stress that first. Look at the original graph first, all right? Because you always need to check, does this pass the horizontal line test? Otherwise, we need to make sure we restrict the domain if necessary, okay? So for this first example here, I'm gonna make sure I turn off my plot, because I still had that on from previous lesson. I'm going to put 1/2 x to the third power, and I'm going to just zoom 6 this to basic window. And the good news is here, when this eventually graphs, we see this does in fact pass the horizontal line test, so we do not have to restrict this. All real numbers is our input, and all real numbers is our output. So for letter A, life is good. Domain and range of the original are all real numbers, which also means the domain and range for our inverse are going to be all real numbers, because these normally flip-flop. So because the domain and the range on the original were all real numbers, the domain and the range on the inverse are also all real numbers for both, because normally they would flip-flop. Well, what we're going to do then is we are going to start by replacing f of x with y, and now we are going to switch x and y. And in order to resolve for our x value, we're going to start by multiplying both sides by 2 to get rid of this fractional value. So we have 2x equals y to the third. And then we must cube root to undo that cube here. So we end up with f inverse of x equals the cube root of 2x. And again, you can always double check this in your calculator as well. You can always look, does this graph look like it is in fact reflective? So we can take, let's see, the cube root here of 2x does in fact look like a reflection over our line y equals x. Graph that and we would see that it looks like it's folded over x. So that's good news there. Presumably I did it correctly. Okay. Now for letter B, we scroll back up here. Letter B, we have x plus 4 to the fourth minus 1. So if we look back here at our graph, we're going to start again by graphing the original. So x plus 4 to the fourth minus 1. Notice on this graph, oops, x. There we go. Notice on this graph, unfortunately, this one does not pass the horizontal line test. Okay, this is not going to pass. So what we have to do is we're going to restrict the original domain so that it's either all of these x values greater than or equal to -4 or less than or equal to -4. So I say we just go with greater than or equal to. That's the one they tend to go with. So if we look at this original graph here, we're going to restrict our domain values so that it is only x values greater than or equal to -4. So now it will pass the horizontal line test if we cut half the graph off. And our range on this one is all of the y values greater than or equal to -1. Okay, so I'm going to write that down. Well, what this means is that for our graph, for our new function, the domain and the range again flip-flop. So now our domain for this new graph is going to include all x values that are the range of the original. So greater than or equal to -1. And the range is going to be the domain of the original. So all of the y values now are going to be greater than or equal to -4. The domain and the range flip-flop. Okay. Now from here, what we are going to see is the function just needs to, like our last problem, be changed to y equals, and then we are going to take our x value and our y value and flip-flop them and resolve for y alone. So we're going to add 1 to both sides. And then to undo that to the fourth power, we're going to fourth root. So these cancel. We're left with the fourth root of x plus 1 equals y plus 4. Last but not least, we need to subtract the 4 from both sides. And I'm going to write the 4 out front of my square root just because sometimes you don't want it to accidentally creep under the square root, or excuse me, the fourth root with the rest of these. And here is our f inverse of x. Okay. Now, without even looking at it, again, we knew what the domain and the range were going to be because we flip-flopped the original one. But to test this out, okay, to double check this, we end up with -4 plus the fourth root of x plus, x plus 1. And if we graph this, again, if we had our line y equals x in here, what we would notice is, again, this is the reflection over that line, so this looks good to go. And again, because we were of that restricted domain, look at our x values are all greater than or equal to -1. All of our range values are the y values greater than or equal to -4. So we can see that, and even looking at the table, we can see that in our table, we're not going to have any values, oops, look at our y values, anything below that -1 is giving us an error message. We can see that domain there. So without even actually looking at our graph, we have the domain and we have the range. This out. Try one more. The next one then we want to focus on is log base 2 of x. So I'm going to use the change of base to type this in. You can also use math alpha math. So log of x divided by log of 2. The same thing as log base 2 of x, right? Because of the change of base. And if we graph this one, the good news here is that we do not have to limit the restriction here on this particular domain. But what we do notice is even though we don't have to make a restriction, the domain is going to only allow us to have all of the x values that are greater than 0. Now our range officially is going from -infinity to +infinity, but remember we can't take log of 0. So on this original function, the original domain here again is anything greater than 0, not equal to it. The range though, all real numbers. So what that means is for our inverse, our domain is going to be the original functions, right? So our domain on this next one is going to allow us to plug in all real numbers, but the range then are only going to be y values greater than 0. And again, we'll see that at the end when we actually find that range. So our original function was log base 2 of x, and if we switch x and y, we can rewrite this. Now you have a lot of options going back to activity 5 when we rewrote this. I like to, you know me, I like to just rewrite this so that we have an exponential with the base of 2 to the x power equals y. Okay, could have also just risen both sides to 2 and this canceled out. Same idea, right? 2 to the x equals y, so that's our f inverse of x is 2x. Okay, and again, to test this out, does this look like we did it correctly? Well, did we reflect over the line y equals x? The answer to me looks like yes. And also check out our domain and our range. We have all x values being able to be plugged in for that red function, 2x, but all of our range values are greater than 0. It does not touch 0. It's just going to get infinitely close to it the more and more negative we get. See, it gets really close to 0, but it's not ever touching it. Okay, just getting infinitely smaller there. All right, and then last example here, all right, one final example. We have example D here, and this particular one then, just to talk about domain and range one more time, we have the square root of x plus 3. Oops. And if we graph it, passes the horizontal line test. So we don't have to worry about limiting the domain and the range, but the original domain, we are not going to have anything less than -3. So our domain of the original here is all the x values greater than or equal to -3. Our range then was values greater than or equal to 0. Okay, so what we have to be careful on here is that when we have for letter D our new domain and range, the new domain is going to be the range of the original. So the range we said was all the y values greater than or equal to 0. And then our range, our our x values on the original we said were greater than or equal to -3. So that means our y values in our new function will be that way. Okay. and our function itself was y equals square root of x plus 3, switch x and y. Reminder to undo a square root, you can square. So we end up with x squared equals y plus 3, and subtract 3 to get our inverse value, right? Now, this is why this restriction from the beginning is so important, because what we're about to see here is we want to make sure that we have these restrictions in place, because if we take x squared minus 3 and here's our graph. Now we limited this because of that original domain. We limited this to only be these x values for the red graph greater than or equal to 0. So that's why we allowed this to happen. We're only going to include this. Your final answer is not including the left half of this graph because we restricted that domain. And again, the range we proved true because it's only those y values greater than or equal to 0. So that's why it's so important to do your domain and range from the beginning, right? Because it'll help you limit this, because otherwise this part is not being included in your graph. Right. To summarize here, a reminder, here's kind of our steps in there. It's also listed out really nicely in the book. It's really helpful to make sure you look at that original functions domain before you even go through and solve it. And solving is not necessarily the hard part. It's understanding those restrictions on the original domain / range and then using them for your inverse. We will work more with this in class, so sorry for the long lesson, but we've made it to the end of Unit 1B. Thanks, everyone.